Wanting students who are good at mental math and growing students who are good at mental math are two entirely different things. In this lesson, we're going to take a look at an example of an instructional process that can be used to facilitate the development of mental math strategies. Last week, we examined a variety of arithmetic strategies suitable for bringing single-digit sums to fluency, and then this week we shifted our focus to working with all addition and subtraction facts within 20. This slide illustrates the strategies that we have featured, but these strategies are not comprehensive. Almost certainly your students will think of additional strategies. The same basic guidelines that we're going to talk about in this lesson also apply to the new strategies that your students propose. First, we need to understand the strategy and think about why it works and whether it works for all numbers or only some numbers. If it's a really meaningful and useful strategy, we can then grow our expertise in using that strategy through some targeted practice. And then finally, we want to incorporate that new strategy into our existing and growing set of arithmetic strategies. In this lesson, I'll describe an instructional process and then use one of the featured strategies here as an example and flesh that out so that you can see what that instructional pathway could look like in practice as you develop that strategy within your learners. So the instructional process that we are recommending here is called distributed practice, which is research-based. Instead of long practice sessions dedicated to a target strategy and then moving on, for example, instead of teaching a lesson on make 10 and then tomorrow doing something different like doubles, instead of doing that, we're going to use short, frequent learning experiences spread over time. That's the power of the number talk. It happens for short 5 to 10 minutes per day, but it happens essentially daily. So that is a very powerful model for growing strategic thinking. We also carefully manage how the target strategy is developed and then how it is merged into the existing repertoire of strategies that a learner has so that it can be accessible in a mixed setting. Now, a process for accomplishing this goal is shown here, where we carefully introduce a strategy in such a way that the underlying mathematical concepts are self-evident to everybody. Of course that would work. Now, that typically is going to require some kind of concrete representation and then some different ways to represent the idea visually. And this whole stage is focused on building these mental images that a learner can reference as they start to apply the strategy and while they're still in a sense-making mode. And those mental images and concrete experiences also allow them to justify that strategy, which is something that they have to be able to do in an assessment mode for Common Core as well. These images help them determine if they're using the strategy correctly, and if two students get conflicting answers, the concrete models and visual representations give them an opportunity to sort of reason out which one must be correct. The concept continues then to be developed through number talks and reinforcement opportunities as it is solidified and then carefully placed into the broader context of mixed review, which is based on strategies that the students will have already learned. The new strategy thus will become an old familiar strategy, although it's a good idea to include some integrative practice opportunities such as problem-solving experiences where they can continue to put that strategy to use, and or occasional number talks which feature that idea to keep that strategy in tip-top shape. I've chosen to use subtracting 9 as the example for this instructional process because I've seen this strategy presented as a number trick without any attention given to the underlying mathematics that makes it possible. And I really want my students to meaningfully understand the arithmetic strategies that they're using. For this reason, it's really good to start with a concrete experience that makes the strategy reasonable. So I might use this scenario just to quickly remind you the nines pattern that we talked about is where you can, if you need to subtract 9, you can subtract 10 and add back 1. So if you just say that to students, it seems a little nonsensical, but we're going to use an experience that makes it really obvious. So I might use the scenario you see here where I have a bag of candy with 20 candies inside. Now previously I've written 20 minus 9 on the board, but I kind of ignore that while I'm doing this little scenario. I say, okay, so I have 20 candies and I'm going to take out 10. So I take out 10 candies and I say, now how many are in the bag now? Again, we're talking about second graders here, so 20 minus 10 should be fairly basic, so 10. And then I pretend to, oh, just now, notice the problem on the board. Uh-oh, wait a minute, I took out 10. Look at the problem on the board. What was I supposed to do? Take out 9. What should I do? Now at this point I think that the average second grader will not say put them all back into the bag and then start counting all over again from 9. I think they'll say, oh, you just have to put one of those back in the bag, then you will have taken out 9. So we put 1 in the bag and I say, okay, so how many do we have in the bag now? I think it will be pretty obvious to them that it's 11 because they just a moment ago told me there were 10 in the bag and I put 1 back in. So again, we're talking 10 plus 1. So then I can act all fascinated about the strategy. Do you realize what you did? 20 minus 9, you just told me, is like taking out 10 and putting back 1. Is that right? Did that work? And so how cool is that? Let's try to figure that out on the board and see why that works. And will that always work? Whenever we subtract 9, does that always work? Let's write this down on the board and see if we can apply it to some other situations as well. So then I would do some visual representations on the board. And again, these visual representations are very intentionally chosen to get the students thinking about the math that's happening. So this visual representation is primarily geared towards helping them understand why it works based on the idea of 9's proximity to 10. So since 9 is so close, if we take out 10, we can compensate back 1 for the 9 that we just took out. So this is building the number line as one aspect of the mathematical reasoning that they can use to justify this and talk about it with other people and explain it. I like to do a turn and talk opportunity at regular intervals so that students are explaining to their partner or their peer how this is making sense and what questions they have. If the students have had experience with number bonds, then I like to use a representation like this where we started with the 20, which we decomposed into a 10 and 10 in the bag, 10 not in the bag. But then I took one of the ones from the 10 that weren't in the bag and also decomposed that into a 1 and a 9 and put 1 back into the bag. So we can represent that with this image, and I can give some labels like still in the bag and removed. And then I use that number bond to construct a sequence of equations. So the abstract, we're going from a visual representation to an abstract representation, but we keep coming back to the number talk. Okay, so to the number bond. So we have 20 minus 9, but the first thing we did was we separated 10, but that wasn't the same as minus 9, was it? What did we have to do? Oh, we had to add back 1. So I write the next one. And then essentially at this point, so what's in the bag? The original 10 that we had in there, and then the 1 that we added afterwards. So it's 10 plus 1, or 11. So I can relate the entire sequence to the concrete candy example using this visual number bond. While it is still fairly fresh in the children's mind, I want to give them a quick reinforcement activity that will give them just a few minutes to ponder that idea by acting it out for themselves. So I might give them 3 or 4 additional subtraction by 9 problems for them to do, along with some counters and an equation template like you see here, so they can plug in what number, so 13 minus 9 or 17 minus 9, and then they can write that as, if it's 17 minus 9, 17 minus 10 plus 1, and think that out to their partner. 17 minus 10 is 7 plus 1 is 8, so 8 plus 1, or 7 plus 1 is 8. So they can use that template and talk about it with their partners and act it out. Now, I don't assume that this short experience is going to solidify things entirely, so that probably is about 10 minutes there, depending on how many of these expressions I have them act out, which is going to depend on how they respond to the strategy initially. And so we're going to need to do some follow-up. And so here's a sample number talk that I might use. You can use occasional number talks like this over the next few days as short, 5 to 10 minute, but frequent learning experiences that keep bringing this idea back to their mind again and again. The expressions in this string are presented one at a time so that when you're finished, the entire sequence is on the whiteboard. Remember, number talks are entirely a time for children to verbalize their strategies rather than you telling them what to think. But you can ask questions to elicit that thinking. For example, after the second expression, you might ask, how do you know that 17 minus 10 is 7? Some children might say, oh, well, I decomposed the 17 into a 10 and a 7. But others might say, well, it's just like that first fact, which would give me a chance to act surprised and say, you mean that addition and subtraction are related? How does that work? Who can explain that to the class? Similar brief dialogues can happen along the way as you proceed, with students justifying their thinking at different steps. The 9 plus 8 fact is not only a chance to explore the relationship between addition and subtraction, but it also offers an opportunity to discuss how the strategy applies to addition. For example, if I want to add 9, then I can add 10, but that was adding too much, so I have to subtract 1. So the relationship, there's also a relationship to an addition version of the strategy, which will make sense if you keep track of where you are in a mental number line. So mental number line, I took a leap of 10. Oops, I leaped too far, so I have to go back 1. The final expression there is accessible to all the learners who can think of fact families, but some of the students might also share how the 9s pattern might be able to be applied to 8 as well, because you could subtract 10 and then add back 2 instead of subtracting 10 and adding 1. So it'll be interesting. You might get an interesting discussion. I wouldn't impose that idea on a student, but some of the students might think of that as a result of this sequence. Students will need a variety of experiences over the next days and a couple of weeks where they get to explore that new strategy. So in addition to the number talks, here are 2 other short tasks that can be implemented. Again, we're not talking about all of these happening on the same day. Distributed practice means short learning experiences on a nearly daily basis, rather than full lessons today on one strategy and then a full lesson on something else tomorrow. So the warm-up game here is a fun activity that can foster students' capacity to take advantage of the unique nature of 9, counting forward and backwards by 9s by using its relationship to 10, and that how to play that little warm-up game is in the teaching resources. And also what you see here is Spokes on a Wheel worksheet, and I've included that in the teaching resources as well. It's sort of like a worksheet that you turn as you take it, and what I have is the template so that you can write in whatever numbers you want. The learning opportunities discussed thus far have been targeted and cued. The primary purpose has been to introduce and reinforce a particular strategy so the students know what strategy they're working on. But the ultimate goal is for the students to have that strategy in their repertoire, to recognize on their own, without us cueing them, where they can use it, and then for them to voluntarily choose to use it. That if an efficient strategy, where it's efficient, where it makes sense, to use it for themselves. And that transition is critical. And for many students, it just doesn't happen naturally. So I'm going to recommend a process by which we can facilitate that transition where a featured strategy can become part of their repertoire that they can apply in a mixed review setting. So here you see an example of a mixed review practice sheet. It's pretty standard. And I'm going to take just a moment to talk about a side issue before we come back to the strategy development. And that side issue is that you see the number combinations here are all provided vertically, and I've been showing them horizontally. So children really need experience with both representations. They need to see things horizontally and vertically and not to be thrown. I've actually run into children who act like it can't be solved when it's horizontal. They think, no, I can't solve it that way. You're going to have to put the numbers on top of each other. And I find that extremely troubling from a number sense perspective. The idea that numbers can only be added when they're vertical and not horizontal is nonsensical. So I like to incorporate the horizontal for a couple of reasons, which I'm going to talk about, even though it is clear that students need experience with both representations. But what advantages does the horizontal have? Well, the horizontal is written as equations and expressions, and students really need to build their expertise with equations and expressions, and that's not obvious in the vertical display. For example, in the vertical display, the bar that you see is really a signal to compute. It's not an equals sign, doesn't look like an equals sign. And so the students need to become increasingly comfortable and competent at working with equations, and the horizontal representation is more advantageous in that respect. A vertical display often sends a message to a learner that they're supposed to use a particular algorithm to respond. For example, oftentimes it's already aligned in such a way that ones are with ones, tens are with tens. I want students to be making those decisions and thinking about them. And I also don't want them to assume, and this is of course when we get into some higher numbers, I don't want them to assume that they are to use an algorithm. I want them to make a decision about whether it could be done through mental math or an algorithm. But what I've noticed is that with students, when you give it to them vertically, they immediately go into algorithm mode. Whereas when you give it to them horizontally, you see a greater variety of students employing some mental strategies as well as some choosing to do it with the algorithm depending on the numbers. So I think it's really good to make a choice. All right, now when I first give them a mixed review, I tell them not to solve any of the equations. I don't want your answers here. Okay, we are not doing answers. Instead, the whole goal is to find which of these problems on this sheet could be solved using our new strategy. That's all, just circle them. Okay, so they'll have it face down while I'm giving the instructions, otherwise some of them will start putting answers down. Face down. Okay, everybody understand we're only circling the ones, and I probably would have a different sheet up that we could have practiced with together so they understand how it works. And then turn it over, and they just circle the ones that relate to this strategy, and then turn it back over upside down. And then when I call on them, I might do some whole group depending on how many times we've done this, or I might have them turn to a partner, share which ones they circled, and decide whether they agree or disagree on where the strategy could be applied. Now, they don't actually have to be in total agreement here. There could be some consensus building. Somebody might discover that they forgot one, but alternatively, somebody might not have, the very first fact you see here is 18 minus 9, and a person might choose not to circle that because they would say, oh, I would use a doubles fact for that. I wouldn't use the nines pattern. And that would be a perfectly reasonable line of mathematical reasoning, so that's fine. So the next thing that would happen is that I would then have them turn it back over again and solve the problems that they had circled, only those, because we're focusing on the targeted strategy. Okay, now we come to a delicate part in the process, and that is where I want the learners to merge the new strategy into their existing repertoire in such a way that they can use it flexibly, like, oh, here I can use this strategy, but over there I can use that strategy. Okay, and that is really, really a critical piece of becoming strategic, but it's also the most difficult because it requires the greatest amount of decision making. So up till this point, I've been taking care of the cognitive load of decision making by targeting it, but now I want to fold it back in and turn over some of that decision making to them, so that increases their cognitive load. And that's why they need to have that strategy solidified before I would do that. Okay, one way to do this and develop that decision making is not to give them mixed review cold, but to do a little preparation for that. And one way to do that is a go, talk, solve protocol. So I give the students a set of mixed facts, similar to what I did in the last activity, but in the last activity they were only looking for the new strategy. Which ones fit the new strategy? Only solve those. Here, they're actually going to classify all the problems I give them according to a strategy they already have in their sort of strategy toolbox, things that we've developed together as a group. And so I would have them first give no answers, leave that blank, but just to write down a strategy code. So would I use a doubles? Would I use a nines pattern? Would I use the count up or count back approach? Whatever we've already talked about, I would give them a mixed review of that. And again, give them an opportunity to compare that to other people and decide whether they agree or disagree. And it's okay at times to disagree. Some facts can be solved more than one way. And then after that, I would have them turn it face down and do a little kinesthetic skip counting activity. And the purpose there is to do a mind reset so that they have to think through their strategies again instead of having stored the first few in their short-term memory. So we'll do a kinesthetic numbers skip counting thing. Maybe do the Macarena as we skip count by fives backwards from 100 or something like that. Okay, then we sit back down, turn the practice sheet over, and solve the equations as quickly as we can, writing our total time at the top of the paper. Now, the goal is just to beat their previous time. They're not in competition with one another. Their goal is to get faster within themselves. I like to use a timer on the smartboard so children can record the time on their paper when they're finished. And I tell them that time is important, but strategy and accuracy is more important. Don't rush so much that you stop using your strategies or you defeat the entire purpose of all the incredibly hard work we've been putting in towards helping you become an amazing strategic learner. All my messages are that strategy is more important than time. We just want to get faster at using strategies, not faster at solving, although that's obviously the result of getting faster at strategies is getting faster at giving answers. But I tell them that we're getting faster at using strategies, not just the answer. Now I continue with this practice over time. Sometimes I will say only solve problems that allow you to use a double strategy or a sum of 10 strategy on this page. Leave the others blank. Let's see who can find them and get the most accurate answers in 15 seconds. Remember, you only get credit for the number combinations that use those strategies. And the goal here is to build awareness so that as they look at a number combination, they think, does it use a strategy? Can I use this strategy? I'm trying to build their decision-making capacity and also the efficiency by which they're making those decisions. I want them not to spend forever making a decision about whether this problem is suited to a double strategy. I want them to make that almost instantly. Yes, I can use it here. And here's another example for counting up, counting back in the nines pattern in a mixed review where they would end up just searching for those and solving those. As we stated in the previous lesson, the most versatile subtraction strategies involve decomposing a number leading to a 10 and using the relationship with addition along with their fact fluency. These strategies take longer to develop than the nines pattern that we discussed because there's more decisions to make along the way. But they are so versatile that it is well worth taking that time to develop it. And you can use the same strategies that we've discussed thus far, except you would need to probably continue that distributed practice over a longer period of time. And this briefly just shows the variety of methods which are color-coded according to the previous slides, which can be employed to solve a traditional fact practice sheet. So as more and more of the strategies become available, solidified, and merged into the children's ongoing strategy toolbox, their fluency will increase. Counting, which is children's fallback strategy, is very error-prone and slow. So as they grow in their strategic thinking capacity, they become increasingly accurate, efficient, and flexible in their number knowledge. And children also need opportunities then to apply that growing mental math skill expertise in more authentic settings. So they need some opportunities to see where they really come in handy. And one of the places where they can really come in handy is solving word problems. Many second grade word problems include number sets that are outside of the range we've been talking about, which is within 20. But the hard one-step problems that we discussed in the first week of this PD module and also the two-step problems tend to have lower number